Hi everyone, we're starting video 18, which is on inverse functions, and that corresponds to exercise or section 14F in your textbook. So before we do that, what I'd like to do is I'd like to quickly go over the different types of reflections that we have looked at so far. We have looked at reflecting graphs over the x-axis, we've looked at reflecting graphs over the y-axis, and we've looked at reflecting graphs over the y equals x, as well as the y equals negative x graph. So let's start with just looking at the reflection over the x-axis. And the reflection over the x-axis tells us that our coordinates, whatever our points are, the points x, y, will go to x negative y. So that our f of x graph, when it is given, it would go to negative f of x. And that means our y values are being affected by this. The x values remain the same. So if I were to quickly draw out a graph, for example, at 2, 2, and then 4, 1, 2, 3, 4, and 4, and then we go to 6 and 2, so that we've got this graph here. So I'm just going to write down very quickly what the points are. So it's 2, 2, then we've got 4 and 4, and then 6 and 2. Alright, so what that automatically tells us that our negative f of x graph, which I'm going to do in red, all our y values are going to change. So that 2, 2 will go to 2 and negative 2. 4 and 4 will go to 4 and negative 4. So it's 1, 2, 3, 4, 1, 2, 3, 4. And our point 6 and 2 will go to 6 and negative 2. So there is our new graph. So this is how we would do this if we were actually physically moving the graph over. And this would be our f at negative x. So we would have 4 and negative 4, 2 and negative 2, and then 6 and negative 2. So our y values are changing. Okay, now if we were to do this type of graph, I'm just going to pick any graph at this point, but if I were to do an actual equation, so I have to get an equation or an image equation. So let's say I have a totally different graph. I'm just going to say y is equal to 5x minus 6, for example, or f of x is equal to 5x minus 6, and I ask you to do a reflection, and it's going to go under m sub x, which means that it's a reflection over the x-axis. Then what that means is wherever I have a y, so I will replace f of x with y. Wherever I have a y, I will replace it with negative y. So y will be replaced by negative y. So that my answer here would go to negative y is equal to 5x minus 6. And because I do not want to have a negative in front of that y for my equation, the negative will be brought over to the other side. So it'll become y equals the negative of 5x minus 6, which is then negative 5x plus 6. Okay, so that would be my first type of reflection over the x-axis. We then have the reflections over the y-axis. So if I were to pick again anything at this point, I could pick this point here, that point there, and this point here, so that I have my graph that looks like this, and my points happen to be 3 and 2, and then 5 and 3 here, and this would be 4 and 1, 2, 3, 4, 1, 2, 3, 4, 5, 4 and 5. If I reflect it over the y-axis, it means that my x values will be changing. So my f of x graph would technically be going to f of negative x. So it means it's my x values that are changing here, not my y values. And therefore, wherever I have a value of x, So 3, 2, my value of 3, 5, and 4, they will go to the opposite sign. So that my graph now in red, f of negative x, will go to negative 3 and 2, it'll go to negative 5 and 3, and it'll go to negative 4 and 5. So that my new graph would be here. My new graph would be right there. And it has been reflected over the y-axis. So it would go to negative 4, 5, it would go to negative 5, 3, and it would be to negative 3 and 2. And my y values remain the same. Now, if I had to do this again algebraically, I'm just going to make up any other function. So I would say f of x is equal to 7x squared minus 3, for example, and it's under a reflection over the y-axis, so it's m sub y, that's a reflection over the y-axis. Then what that means is wherever I have an x, I will replace it with negative x. So y will equal 7 times negative x all squared minus 3, and that's going to give me, lo and behold, 7x squared minus 3, which is exactly the same graph I had above. Now, why does that happen? I'll just give a brief explanation on that. What I have above, what I have rather off to the left, is, to the right, is I have a parabola. And if I take a parabola and I reflect it over the y-axis, I hope it's clear that this black part of the graph on this side would get reflected over to this side, and the other side would be reflected over to the other side, which is really just giving me exactly the same graph. Okay, so the next one we're going to look at is the reflection over the y equals x line. Now, I'm just going to briefly take, a point. So I could take, for example, the point, let's take negative 1, 2, 3, 4, and 1, 2, 3. So negative 4 and 3, rather than just plugging in an entire equation or an entire function. I'm just going to take a point. If I take the point negative 4, 3, okay, what is basically happening when I reflect it over the y equals x line is that my xy values are going to swap their positions and they're going to become yx. So essentially what that means is that my point negative 4, 3 is going to become 1, 2, 3, and 1, 2, 3, 4 down. It'll go to 3 and negative 4. That would be my reflection over the y equals x line. So m of y equals x would be reflected as such. Okay, so 3, negative 4, 3 would just become 3 and negative 4. I swap their positions. Okay, now that would take care of how I would reflect something over the y equals x line. Now, when I want to reflect over the y equals x line, which we just did, I can also do that algebraically. And we did that already. We've already done this algebraically in the previous sections. So that I could take, for example, f of x is equal to 4x minus 9, okay? And I would say, okay, reflect this under the m sub y equaling x. So it's a reflection over the y equals x line. And what did we say we would do? Because we're swapping the positions of the x's and y's actually physically over the graph, so that y is equal to 4x minus 9 means that I am going to swap my x for y, and my y for x. So swap x and y values, okay, or the x and y coordinates, okay? So what that means is that wherever I have a y, I will replace it with x. So in the given problem, y equals 4x minus 9, my y will be replaced by x, and my x will be replaced by y. Here it is. Y goes to x, x goes to y. And now, because I don't leave my answer with x equals, but we always write our answers as y equals, then I'm going to isolate for y again. And therefore, I'm going to end up getting x plus 9 is equal to 4y, and therefore, y is going to equal x plus 9 over 4. Or, if I want to simplify that, I could write it as 1/4 x plus 9 over 4, just to show that it is a linear equation. This is a linear equation with a slope of 1/4 and a y-intercept at 9 over 4. Okay, so having done that, now I can officially say that when I am reflecting a line over the y over equaling x line, that function is now called an inverse function. And the inverse function is denoted as being f negative 1 to the x, or g to the negative 1x, or h to the negative 1, or f inverse, g inverse, or h inverse. So if I were given now a problem that said f of x equals 3x plus 5, and I ask you to find the new function f inverse x, that means that I am asking you to tell me what the new function is once it has been placed over the y equals x line. The new function would be over the y equals x line. So algebraically, it means that I'm going to be doing this. I'm going to be rewriting f of x as y equals 3x plus 5, because recall that f of x is the same thing as y. I then swap the positions of x and y so that x is going to equal 3y plus 5, and then I'm going to isolate for y again. So we always like to write our answers as y equals. So that I'm going to say x minus 5 equals 3y, and therefore y is equal to x minus 5 all divided by 3, which, if we want, could be rewritten as 1/3 x minus 5 over 3. I just write this so that I understand that my slope is 1/3, and I know that my y-intercept is negative 5 over 3. But again, it's not essential that you do that. And then the very last thing you want to do once you've gotten to this last part where you've swapped your x's and y's and you've isolated for y again, then the last thing you want to do is you want to rewrite that y as f inverse x equaling x minus 5 over 3. So there is your inverse function. So the inverse function is nothing more than placing your original function over the y equals x line. Okay, and so it's a reflection over the y equals x, or the mirror image over the y equals x. Now, what we're going to talk about, though, a little bit more in depth, is the whole issue of does every function actually have an inverse to it? Now, let's take a look at an example that I'm going to write out here now. Here's an example of when I'm going to do y equals x squared. Let's take y equals x squared as an example. So I'm going to do 1 and 1. These are my x's along the x-axis, my y values, and this is my origin. And I'm going to choose some points. I'm going to do f of x is equal to x squared. And I'm going to ask you to find the inverse of it. Okay, so we're going to do it physically first, and then we'll do it graphically. We'll do it physically first, and then we'll do it algebraically. So if I choose some points for x and y, although we should already know by now what the x squared graph looks like, I'm going to start with -2, -1, 0, 1, 2. So I know that -2 squared goes to 4, -1 squared is 1, 0, 0, and 1 is going to go to 1 squared, and 2 squared is 4. So I do -2 and 4, negative 1 and 1, 0, 0, 1, 1, and then 2 and 4. And there is my y equals x squared graph. Alright, now, if I take the inverse of that, the inverse means that I swap my x's and y's. So my point of negative 2, 4, my point negative 1, 1, 0, 0, 1, 1, and 2, 4, if I put them over the y equals x line, which I'm going to do right now, as starting from here, if I put them over the y equals x line, the y equals x means that when x is equal to 1, y equals 1, when x equals 2, y equals 2, when x equals negative 3, y equals negative 3, and so forth. Okay, so all I really need to do in making the inverse function is just put it over the y equals x line, so that negative 2, 4 would go to 4 and negative 2, so starting over here to the left, so negative 2, 4 would go to 4, 1, 2, 3, 4, and negative 2. Negative 1 and 1 would go to 1 and negative 1. 0, 0 will stay exactly where it is. 1 and 1 will stay exactly where it is. And 2, 4 will just go to 1, 2, 3, 4, and 2. Done. So that we know that our inverse function is right here. This is our f. This is our f inverse x. Okay? And our original was f of x here. So we know y equals x squared is our original, or f of x function. Okay, y equals x squared, or f of x equals x squared. Okay, now, when I look at this inverse function, the first question I should be asking myself is, but when I take the inverse of my original function, y equals x squared, if I perform the vertical line test on this, does it actually give me a function? Because remember that we said that the vertical line test determines whether a graph is considered a function or not. And we said that for every value of x, there could only be one value of y. It could be a one-to-one relationship. And if I perform the vertical line test on this graph right now, okay, I'm going to do that in green. If I perform the vertical line test on this, what I see happening is that my red graph, or my inverse function, is not a function at all. It's not a function because for every value of x that I have, I'm getting two values of y, and that can't happen. So technically, the f of x function, or the f of x function in this case, the f of x being in this case x squared, well, it does not have the inverse is not a function, because when I perform the vertical line test on it, I discover that the inverse that I'm physically doing, the red graph, it's getting two values for y for every value of x. So I say that the inverse is not a function here. But the bigger question might be at this point, well, is there any way that I can actually make the inverse function, not the inverse function, but is there any way that I can make the inverse of x squared into a function? How do I make it into a function? So, taking a look at it, I could say, well, one way that I could turn this into a function is by allowing the inverse to be a function, is by removing the bottom part of this graph. The bottom part of this graph, as you can see, I've just taken it out, corresponds to which part of the graph on the original f of x? Well, it seems to correspond to this blue part here that I'm erasing. So that if I erase, or I take away from the x squared function certain values, well, then my x squared graph would be considered a function. So what that means basically is this, that if I put a restriction on my domain So this is where domain comes back into play. If I put a restriction on the domain, and that restriction would have to be that x is such that x must be greater than or equal to 0, then yes, my graph does exist as an inverse because I'm not getting that it's not a function. It is not failing the vertical line test because I'm getting for every x value one value of y. If I don't make the restriction, let's go back, I'm going to put a dotted line here. If I don't make the restriction that x has to be greater than or equal to 0, and I allow the negative part of this graph to exist, then that means that I'm allowing the negative part of this graph to exist, and it's no longer considered a function, because for every value of x, I'm getting 2 values of y. So the moral of the story basically is that y equaling x squared does not have an inverse to it unless I put a restriction on the domain. So if I put a restriction on the domain and say that the values of the x have to be larger than or equal to 0, then yes, it is considered a function because it passes the vertical line test. If I don't put a restriction on the domain and I allow every value of x to exist, including all the negatives on the left-hand side of the graph here, then those negatives on the left-hand side become the bottom part of my red graph, and therefore it's no longer a function. So with a restriction on the domain, yes, x squared does exist, and yes, it does have an inverse. If I don't put a restriction on the domain, then that means that no, x squared is not a function, and it does not have an inverse. Alright, so having said that, let's take a look at, though, algebraically, what would happen. So if I take, algebraically, I say f of x is equal to x squared, and I now say find the inverse. Okay, I say find the inverse, or find f inverse x, given that f of x is equal to x squared. So what I do is I say y equals x squared. It's like the previous questions we did on the last page. I swap my x's and y's. X equals y squared. And then I isolate for y, so that I get y has to equal the square root of x. Do we all see here that y equaling the absolute, equaling the square root of x, that is my inverse. Okay, f inverse x does equal the square root of x. But what's our restriction here? The restriction is that I can't have any values of x that are less than 0. I'm allowed to have it equal to 0, but I am not allowed to have it less than 0, because I can't have a negative number under the square root sign. So therefore, I can say f inverse x is equal to the square root of x. But there must be a restriction on the domain where x must be greater than or equal to 0 in order for the inverse function to exist. Alright, now, the other thing that I want to discuss, there's just a couple of other things that I want to discuss, and then we can, and then I'm done. So that the next thing I want to discuss is that instead of having to find the inverse function and graphing it, what I can do to get the inverse, so swapping my x's and y's, what I can do, instead of doing the vertical line test on the inverse function, what I can do is I can perform what is called the horizontal line test on the original f of x function. And if I am getting for every x value one y value, then I can say that the function has an inverse to it. So for example, in this first example here, I've got a linear equation, and if I perform the horizontal line test on it in several spots, so I could perform the horizontal line test on several spots here, on the first one, I see that for every x value, I'm getting one value of y. So therefore, yes, this is going to be a yes, where it's yes, there is an inverse. There is an inverse function. Okay? Now, if I perform it on this parabola here, I do the horizontal line test, and I'm getting two values of y for the two values of x for every value of y, and therefore that's not good. So that means that it's a no. There is no inverse function. But again, there is no inverse function if I am not given any restriction on the domain. So here, I was not given any restriction on the domain. I see the graph physically, and therefore I say, nope, because I am getting two values of x for each value of y in this case, then that means there is no inverse function. And the same thing occurs on the next one. On the next one, I've got another function, and again, performing the horizontal line test, it's touching at more than 1 point for every horizontal line that I put through. So therefore, the answer is no here as well, no inverse function. But again, that is going to be true if I put a specific restriction. That is going to be true only if I don't put a specific restriction on the domain. Alright, now, if we talk about inverse functions, so we've gone through the inverse function, and I've shown you how to graph it, and I've shown you how to do the inverse functions. So if I give you, for example, f inverse x, find f inverse x, and f of x equals 3 minus 5x, then we said the procedure is we rewrite as y equals 3 minus 5x. We then swap our x's and y's, so x is equal to 3 minus 5y, and then we isolate for y. So then I will say 5y is equal to negative x plus 3, and therefore then I divide both sides by 5, so I get negative 1/5 x plus 3/5. Plus 3/5, or I could write it as negative x plus 3 over 5. Same thing. Okay? Over 5. And now my last step is to change y into f inverse x is equal to negative x plus 3 over 5, or negative 1/5 x plus 3/5. Alright, so we said this is the way we do our inverse functions. Alright, now, when we are looking at, though, working with composite functions, okay, and which is f inverse, or f, like we looked at f and f of g, or g of f of x, or what if we do now f of f inverse, for example. So a function may or may not have an inverse, and it's going to be determined by several things. Okay? So if y equals f of x has an inverse function, so if it does have an inverse function, so if a function has an inverse, okay, then the new function is going to be called f inverse x, and we've already determined that. So the new function, the inverse of it, will be s to the negative 1 power x. Now, the inverse must satisfy the vertical line test. So it's what I mentioned before. If I have this function, I redo it over the y equals x line, it goes like this. That's the inverse, but when I put it through the vertical line test, it fails it, and therefore it's not considered a function. It's not considered an inverse, or it doesn't have an inverse. Now, we know that it's going to be a reflection over the y equals x line, okay? And the other important thing is that, this is the most important thing, is that when I perform the composite function of f inverse, well, my answer would always have to equal x. So if I am determining that something is a function, okay, or that it has an inverse function, then that means that if I do f of f inverse, or if I do f inverse of f, my answer coming out of that should always be x. Okay? And this is going to be called the identity function. Okay? So when f inverse of f, or when f of f inverse equals x, then that is called the identity function. Okay, it's a specific term that we're using. So when f of f inverse or f inverse of f both give you the same answer of x, then that's defined as an identity function. All right. Now, if xy then lies on f, then yx has to lie on f inverse. And reflecting the function in the line y equals x, it has the algebraic effect of it's going to interchange x and y. So x becomes y becomes x. And this brings us always back to the concept that we already touched upon way back several weeks ago, where we can basically say that if, for example, y equals 5x plus 2, then the inverse is going to be x equals 5y plus 2. So I've swapped my x's and y's. Does everyone see? I hope that everyone understands that the domain of the inverse function is going to be equal to the range of the original function, and vice versa. The range of the inverse function would have to be equal to the domain of the original. So the domain of the original is going to equal the range of the inverse, and the range, the domain of the inverse would equal the range of the original. Okay, and this is what our graph would look like. So if I took any f of x graph and I reflected it over the y equals x line, well, this point would be over here, this point will go over here, and therefore they are swapping positions, okay, and therefore the range of one function becomes the domain of the other, and vice versa, okay? All right, and again, we can talk about this further in class, about the f of x function being equal to x squared, because that's a particular function. And like I said, this is the explanation. I'm just going to leave this on for you. You can stop the video and read this off if you want, but this is what I discussed no more than 15 minutes ago, where I said the x squared graph has a function, it has an inverse if I put a restriction on the domain. And there it is. So if I get rid of this part of the graph, that means I'm getting rid of also that part of the graph, and all that remains is this part of the graph here and this part of the original graph, and both of these are considered functions. They both pass the horizontal line test and the vertical line test. And therefore, in this particular case, y equaling x squared does have an inverse to it because I've placed a restriction. There's my restriction on the domain. X has to be greater than or equal to 0. Okay, so domain restrictions are going to be a key point here. Now, the very last thing I want to do is just go over one question. I don't think I'm going to insert any questions on this video because there's a lot, it's 33 minutes long. So let's just do one more question. It says two functions f and g are defined by f of x equaling 7x plus 1, where x is an element of R, and g of x is equal to x over 3 minus 1, where x is an element of R. So there's my domain. It says, find the inverse functions f of inverse x and g inverse, and verify that f of g at -1 is the same thing as saying g inverse of f inverse. Okay, so what I'm going to do first is I'm going to do g inverse and f inverse first. So I'm going to take f of x equals 7x plus 1, and I'm going to say y equals 7x plus 1, and I'm going to swap my x's and y's. So it goes to x is equal to 7y plus 1, and then x minus 1 is equal to 7y, so that y is equal to x minus 1 over 7. And therefore, f inverse x is equal to x minus 1 over 7. there's my first thing that I found, f inverse. So I've taken care of this part here that I've just circled. I'm now going to do g of x. So g of x, I know, is equal to x over 3 minus 1. I will rewrite it as y equals x over 3 minus 1. Swap. So my x is equal to y over 3 minus 1. And now I'm going to do x minus 1 equals y over 3. And isolate for y, so that I get 3x minus 3 equals y. Therefore, g inverse x is equal to 3x minus 3. So I've taken care of f inverse and g inverse. Now, we need to prove that if I do f of g and I take the inverse of it afterwards, it's going to give me the same thing as doing g inverse of f inverse. So, here we go. This is getting to be the hard part. So I'm going to do f of g first, because it's inside the parentheses. F of g means that I am taking g of x and inserting it inside f of x. So I'm going to do f of g first. I'm going to do this now in another color. So I'm going to do f of g first of x, and that means that I'm taking g of x and inserting it inside of f of x. So it's going to be 7 times x over 3 minus 1, and then it's plus 1. And that'll give me 7x over 3 minus 7, and then plus 1. I will take a common denominator, so it'll be 7x over 3 minus 6. Common denominator giving me 7x over 3, and it's minus 18 over 3. So I just got a common denominator. So there's my f of g of x. Now, if I now do f of g of the inverse of that, it means I'm taking this f of g of x, and I'm going to do the inverse of that. So that means it's going to be y is equal to 7x minus 18 all over 3. Swap my x's and y's. X is equal to 7y minus 18 over 3. So it becomes 3x is equal to 7y minus 18. And it'll become 3x plus 18 is equal to 7y, so that y will equal 3x plus 18 all over 7. Therefore, f of g of inverse is going to be equal to 3x plus 18 over 7. Now, I've taken care of this part here. I've done f of g of inverse. Now, I'm going to do g inverse of f inverse. So what does that mean? I'm going to take the f inverse, which we found originally here, and I'm going to replace it inside of g. So wherever I have an x in g inverse x, I'm going to replace it with x minus 1 over 7. So that's going to go in here. So that I will say g inverse of f inverse is equal to 3 times x minus 1 over 7, and that's minus 3. And that equals 3x minus 3 all over 7 minus 3. I'm going to get a common denominator here of 7, which gives me 3x minus 3 3x minus 3, hold on. Okay, so that it would give me 3x minus 3 all over 7 minus 21 over 7. Okay, now I have just caught an error that I did way back at the beginning here. There's a small error, and the small error was that when I brought this negative 1 up here over to the right, to the left-hand side, it should have been plus 1. So all of this should go to 3x plus 3. And there should be a plus 3 here, a plus 3 there, and a plus 3 there. And now, when I simplify all of that, it goes to 3x minus 18 over 7. And there's still an issue because, okay, so the issue that I have just discovered is that, okay, the right-hand side of our equation is correct. It is 3x plus 18 over 7. Now, the issue that has been created is that in the original left-hand side, when we were finding f inverse x and g inverse x, I made a small error in the g inverse x. So when I had up here, so where I've put the star up here, I was supposed to have, so it was x is equal to y over 3 minus 1. When I brought that minus 1 over to the other side, it should have become plus 1. And therefore, as a result of that, I should have ended up with 3x plus 3 as my g inverse x. Now, because of that, what also got affected was when I did g inverse of f inverse, this negative 3 here should have gone to plus 3, and this should be a plus 3. And as a result, that negative 21 should have gone to a positive 21. And therefore, that gave us then 3x minus 3 plus 21, which gave us plus 18. And now we see, if we take a look at the two, we have g inverse of f inverse is actually equal to f of g inverse. Okay, so we have the same answer of 3x plus 18 over 7 and 3x plus 18 over 7. I apologize for that mix-up. I forgot to put, I placed a negative where it should have been a positive, and that changed my answer by a little bit. And that's why I went back to take a look at it, because I realized that the two had to be the same, and I made a small error in the addition or subtraction. Okay, I would say that after 42 minutes, I think we've had enough. We will go into the next section next time. See you next time.